Hello. How are you all? Let's see, I'm gonna Eddie, how are you?
Good, how are you?
I'm doing well, thank you. Hi, Felicia.
Yeah, I guess I could.
Yeah.
Christopher, unplug me.
Unless you want to hear our session.
So, let's see, what are you guys working on? What do you want to talk about?
I mean, you could talk.
Right.
No, you only have the listening option.
You have it on
That's
the front?
weird.
On the front?
Hey, Eddie, let's see, what are you working on this week?
I'm doing better this week, but I have one particular problem that I'd like help with.
Yeah, sure, let's look at it. What is it?
Okay, it's section 4.3, number 36.
Now, again, I am looking at an older edition, but I doubt that it's changed much. But
Yeah.
now, if this just happens to be a problem that's drastically different, you let me know. But 4.3 to number 36.
It says it's from the 7th edition, I think is what the homework's from.
Yeah. What does your problem say?
Sorry. Okay, the freight train cars.
Oh, okay, now this is.
No, wait a minute. I may be wrong with that.
Mine says something about customer purchases. It says like in a department store, there are 120 customers.
Yeah, I don't think that's it.
Yeah. Well, then I guess I could go into our course and look at the PDF, but you know what? I think it's going to be easier if you just kind of tell me what the problem is.
You know what? Let me grab my sheet. And if Felicia has a problem, it's okay to go ahead. I grabbed the wrong sheet, and that was not the right number 36.
Okay. Well, then, Felicia, did you have a problem you were working on that you'd like for us to discuss?
Okay. Is she talking?
No. I'm not sure if she's active right now or.
Okay. Okay, this is a different 36. It does say section 4.3. It's about Olympic medals.
Oh, okay. Yeah, I see it. I have that problem. Yeah.
Medal distribution.
Can y'all hear me?
Yeah.
Okay, I see it.
He's gonna work on it.
Now, again, I'm just going to work under the assumption that the numbers that I have in this edition are the same or similar to yours, but in mine,
Headset's hot, Ed. So the headset's hot.
Alicia, did you have a question? I guess not. So, can you tell me like what you've started on with the problem and where you left off and?
Well, this is one problem I didn't get far on at all.
Okay.
I just thought I found this. I don't know if that is correct.
For some reason now your screen is really small. Let me.
Really?
See if I can.
Oh, that was my own letter.
Okay, there it is. Can you put it up there again for me?
Yeah, I think I kind of did that on my own now that I'm thinking the G for gold and then the US metals. I don't know. I was trying to work.
Oh yeah. So so that you have like a conditional probability there. So why don't we just start from the beginning with this one?
Okay.
And so it looks like that there are 3 parts, A, B, and C. Let's just look at part A and then see if we can figure that out, and then we'll move on from there. But can you read to me or tell me what part A asks you to do?
Find the probability that the winner won the gold medal, given that the winner was from the United States.
Okay. So this is a conditional probability. There is a formula that we could use to calculate conditional probability. When you have your data in a table form like this, though, oftentimes you can skip the formula and just go directly to the table.
Okay.
And I think this is a situation where that's going to be true. So in the problem, they say that it's a given that your medalists are from the United States. And so we're no longer considering everybody in the world, who won medals. In this case, we've narrowed that down. And so our entire pool are just those medalists from the United States. So how many medalists are there if we only look at those in the United States?
103.
And how did you get that?
I added the gold, silver, and the bronze just from the United States.
And just to make sure that we have the same numbers, can you tell me what those numbers were that you added?
35, 39, and 29.
Yeah, I'm glad I asked because those are different from what I had in this edition. So 35 plus 39 plus 29.
Yes.
Okay, so those are all of the medalists from the United States. Now, of those, how many were gold medalists?
35.
Yes. So if you only consider U.S. athletes, who got medals, your pool is 103. Now, if you narrow it down to those 103, what's the probability of selecting somebody with a gold? Well, it'd be 35 out of the 103. So, does that make sense?
Yes, maybe I was trying to make that more difficult than it was.
Well, I don't blame you, or I completely understand why. We could do it another way using the formula, and it's a lot more complicated.
No,
But when you have something in a table actually this is called a cross-tabulation, really you can avoid a lot of that busy work because you can narrow things down to either just a column or just a row. Just remember, in a conditional probability, you narrow your pool. You're no longer selecting from the entire population because something has been decided, and that has narrowed your pool. In this case, it was given that the winner was from the United States. So we've automatically ruled out the possibility that they were from Russia, China, Great Britain, or others. And so our entire pool now is just those 103. So yeah, it's 35 out of 103.
That completely makes sense. Okay. And
Yeah. Okay.
Okay.
Now, I don't want, now that we've got the answer, and that's like I've shown you the intuitive or easier way to do it.
Mhm.
I want to just show you what the formula for that would look like, okay? So we're looking for the probability of gold given US. That's the probability of gold and US over, I'm going to hold this up here. Can you see there what I've said? Probability of gold and US over the probability of US. Now, this is the actual formula for conditional probability. Now, if we use this formula, we're going to get the same answer.
Okay.
And I want to just show you that. How many people are in this category where they are gold medal winners and they're from the United States?
How do I make you full screen? Do you know?
How do you make me what?
Full screen.
Oh, here, you know what? Let me see. I think I can control that.
Okay.
Am I a bit? Is that right? Okay.
Thank you.
Now let's look at it again. You see here? There's the abbreviations, the probability of gold and US over the probability of US.
Okay.
So for this, that's the definition of the formula for the conditional probability of gold given US. So in the numerator here, gold and US, those will be people who are simultaneously US athletes and gold medalists. Now, in your version, that would be 35. Now, again, my numbers are slightly different. In your version, Eddie, what's your total of all medalists?
Gold, silver, and bronze?
And regardless of country, just the grand total. You'll have to look in your book.
1, 2, 3. No, I don't know. You mean like from all the countries? Gold, silver, and bronze?
Cumulatively. So if you add up all the medal winners from every country and from all
medals.
All medals.
Okay, can you give me just a second? $729.
729.
729.
Okay, so let me go back to my work here. I want to show you something. So the probability that you would select somebody who's a gold medal winner and a U.S. athlete, that would be 35 out of 729. There are 35 people who satisfy both of these conditions simultaneously. They're gold medal winners from the United States. Now, that's out of our grand total. Now, the probability of selecting a U.S. athlete, is regardless of their medal, that would be the 103 out of 729. Now, notice when we simplify this, we've got a fraction over a fraction. That you would invert and multiply. Basically, what's going to happen are these two denominators are going to cancel out. So we'll end up with 35 over 103.
Got it.
And notice that's what we decided the answer was from the get-go, was 35 over 103. So I just wanted to point out that you can use the formula for conditional probability, which is this fraction of the probability of, this is a union, the and statement, over just this basic probability, but you'll get the same result. So you can kind of avoid this step and go straight to the answer when you have your data in a already tabulated. Okay, let's look at the next part, which is part B. Can you tell me what that says?
Find the probability that the winner was from the United States, given that she or he won a gold medal.
So this kind of time we're reversing it about as far as what's the given.
Okay.
So in this case, it's given that there are gold medalists. So we're only considering in our pool gold medalists. How many gold medalists are there altogether?
103.
No. We're not just.
Oh, not United States, sorry.
We're just how many gold medalists, regardless of country.
Yes, let me go back.
244.
Yes.
Okay, excellent. And so, when you have a conditional probability and something is given, you have narrowed your pool to only include the people that have that given condition. In this case, they are gold medalists. So we're only considering gold medalists now. Now, of all of our gold medalists, how many are from the United States?
35.
Yeah. So what's the probability of picking a gold medal, picking a US athlete, given that you're only considering gold medalists? Well, 35 out of the 244.
Okay. Yes. I was making this way more difficult than what it is.
And again, if you use the formula, you get the same answer, but it is a little bit more complicated. So I just like to point out that when you have things in a cross-tabulation here, use that. Things are already kind of separated out, in columns and rows, and that makes this a whole lot easier. Okay. Now, what about the part C?
Okay, it says, are the events, quote, medal winner is from United States, and, quote, gold medal won, independent. Yeah, independent.
Yeah, and how are we going to, what's our test for independence?
I don't know. Can it stand on its own?
Well, there's a certain rule here that says, I'm going to just write this down for you. Okay. Give me 1 second. Okay, I wrote it down in this box. So it says, and I'm just using A and B as labels for generic events. It says, if the probability of A, or how did I write it? Yeah, if the probability of A given B is the same as the probability of A all by itself. If those two things are the same, then the two events are independent.
Okay.
Now, in this particular question, if I wanted to rewrite this using labels that kind of match up here, I would rewrite this as say, if the probability of US given gold equals the probability of US, and you can do it the other way if the probability of gold given US equals the probability of gold. I'm going to write this. Show this. Here I've modified what I said here kind of generically. I'm saying if the probability that the athlete is from the US given that they are a gold medal winner. If that's just the same as the probability that they're from the US, then those two things are independent. Now, you can reverse the conditional, but in that case, I'm going to compare it. If I use the probability of gold given US, then I'm going to compare that to just the probability of gold. Now, we have already calculated both of these things, both of the conditional probabilities. The probability of US given gold, that's what we just did. That was 35 out of 244. And in part A, we did the probability of gold given US, and that was 35 out of 103. So we can use either one of these. Now, if we use the top one, we need to compare this to just the probability of picking a US athlete. Now, the probability of picking a US athlete, there were 103 of them, and our total for all athletes was 729. I'm sorry, my pen's kind of going crazy on me here, but might have to get a new one. So here's the things that we need to compare. This probability that they're from the United States, given that they're a gold medal winner, that probability we calculated as 35 out of 244.
Mm-hmm.
So we're going to compare that to just the probability of getting a US athlete. Well, there were 103 out of 729. Now, we probably might as well use our calculators to convert these to decimals. This one I already did, it was about 14%. And if you take 103 divided by 729, that's also about 14%.
Mm-hmm.
So these are, for all intents and purposes, equal. Now, those are both about 14%. So in my case, if they are equal, then that means that these events are independent.
Okay.
Now, I would usually tell my students so like in this case, in one instance, I got 14.34. And in the other, I'm sorry, or 0.1434. And in the other calculation, when I took 103 over 729, I got 0.1413. Now, those are the same up until the 1,000th place, the third decimal digit. To me, that's close enough where I say, yeah, those, I'm going to just say that they're pretty much equal and say that these are independent. Now, of course, they are not exactly equal, but to within a percentage point, they're the same. So for me, that's enough to say that they are independent.
Okay. Thank you very much.
Yeah.
That's all I had this week.
Felicia, if you have anything that you want to work on, just speak up and let me know. This is really, I kind of leave it up to you guys to run the show or let me know what you want to discuss.
The problem we just worked on was the one I was working on and having trouble with, so.
Oh, okay, well, that works out. Do you feel like you have a pretty good handle on it now?
Yes.
Yeah, the formula, like you said, makes things a little bit more complicated than they need to be. So I think I just need to practice the formula more than anything.
Yeah, again, now if our data wasn't already organized in a cross-tabulation like this, we would really need to use the formula. And like I said, you can still use the formula here. You'll get the same answer. But you might as well take advantage, if you have things in a cross-tabulation, you might as well take advantage of that in calculating conditional probabilities. Give me one second. I'm going to turn out that light that's behind me
Okay.
so that it's not, there's not like that sun in the background. There we go. All right. So what's the next question we can work on?
Going backwards a little bit to section 4.1, number 36, tossing a coin and rolling a die. We were supposed to draw a tree diagram to determine the outcomes.
Oh, yeah, okay.
A coin is tossed. If falling heads up, it's tossed again. If it falls tails up, a die is rolled. I've worked on drawing the tree diagram, and it feels like it could go on for eternity.
Oh, interesting. If it falls tails up, a die is rolled. Okay. That's funny. I understand. I can guess where this is going, but can you show me how you started your tree diagram? Oh, actually, Felicia, you've got heads, tails, and now, okay. So when I look at your tree diagram, you got that for that first coin toss, Felicia, where you have the two branches, heads and tails. Now this says, if you get heads, you're going to, to go again. So I agree that you should have the two more branches, heads and tails. But now for that branch, it's going to stop right there. So I understand the way that this is phrased, you could interpret it, say that it's just going to go on and on forever. But I really think the intention here is there's going to be at most a two-step process. So you're either going to flip a coin, and get heads, in which case you're going to flip one more time.
Okay.
Or you get tails, and you're going to put your coin away, and you're going to get out a die and roll the die. So for the branch that starts with the tail, to represent the roll of the die in the second step of that process, we're going to have, well, let's see, when you roll a die, what are the possible outcomes?
1 through 6.
Yes. So that branch, the tail branch, is then going to have 6 branches that kind of spring forth, or I don't know how to phrase that exactly, but so let's see if we can revise that.
Enough is enough, dude. How many fucking times do you need to hear a fucking rock?
Right. Take the same bird.
So, do you have a revision to share? Okay, let me make your screen bigger.
Or did I add one more? One too
So,
many.
okay, let me, I'm going to put my screen up for just a second. And let me show you what my thinking was here.
Okay.
This represents our first coin toss. There are two possibilities. You're either going to get heads or tails.
Right.
If you get heads, you're going to flip the coin one more time. So there are two possibilities in that coin toss, heads or tails, and then you're going to stop. Now, if we go backwards to the first coin toss and we go down this path where we get tails, we're going to put the coin down and we're going to pick up a die, and we can either get a 1, 2, 3, 4, 5, or 6. So when I think about the different sequences of outcomes, I could either get heads and then heads, because I had a heads on the first coin toss, and so I did it again, or I got heads on the first coin toss and then got tails. So I either got heads, heads, or heads, tails. Now, on the other hand, if I were to get tails on the first coin flip, I would roll a die and I could get a 1. So there's T1. Or I could get tails followed by a 2 on the die. Tails followed by a 3 on the die. So as far as all the possible sequences, there are 1, 2, 3, 4, 5, 6, 7, 8. 8 possibilities when I consider the two-step process. 8 sequences. And I'm just using H for heads and T for tails.
Okay, that makes sense.
Yeah, that question was phrased where you could easily read it to say, yeah, this just goes on and on forever. Every time you get heads, you're going to just keep flipping the coin. And every time you get tails, you're going to roll a die. And so for the path of heads, it would just go on forever. But I think they really meant for this interpretation, where it's a maximum of 2 steps. Either you're going to flip a coin twice, or you're going to flip a coin once, followed by the roll of the die.
Thank you for that.
Yeah, no problem. That was a good question. Because the wording there, yeah, was tricky. The T diagrams are really helpful when you have a multi-step process. It allows you to enumerate all the sequences, that can of your outcomes. So in this case, once I had them all listed there, if I said, what's the probability that someone would get heads followed by heads on a coin toss, they have it end up with an HH basically. Well, you say the probability, well, there's only one way that can happen. 1 out of the 8 possibilities. So the probability of this is 1 out of 8.
Well, that's all I had. I guess I'll start on 4-4. I haven't even gotten a chance to look at it, so I don't have any questions yet.
Okay, I'm just going to glance ahead and see what 4-4 is about. Well, those are counting rules. Ah. You know what? I might be able to give you a few pointers on that just to get you started.
I will take any pointers I can get.
Okay. So in these counting rules, basically, it comes down to two important formulas: permutations and combinations. And they're closely related, but it is important that you're able to distinguish between the two. And so let's start with, well, your book does permutations first. And so let's start with that. So I'm on page 236. Again, this is in the 6th edition of the book. That's not going to change anything about the definition of a permutation. But in the middle of that page, it says the permutation rule: the arrangement of n objects in a specific order using r objects at a time is called a permutation of n objects using r objects at a time. And then we're given this formula for calculating the permutation. And we'll just write it down in my notebook so that I can put it up on the screen. Here's that formula that we see. These are like subscripts, the N and the R, and that's capital P. So if you have n objects, and I usually think like this is in a pool of from which I can select things, and I'm going to select R, and there's a specific ordering. Then my formula, I take n factorial and n minus r factorial. Now the factorial here, this n with the exclamation point, when you have an integer and you're taking the factorial, you're basically taking that integer and multiplying it by every other integer that's less than it until you get down to 1. I'm going to illustrate this with an example. I think that's going to make things clear. Let's say that I have a class with 8 students in it, and I'm going to award medals to winners of some sort of competition. And so I'll have a gold medal winner, a silver medal winner, and a bronze medal winner. So I've got 3 spots to fill. And I only have 8 students. Now, the ordering here is significant. For instance, if I select my student to win a gold medal, that's different than if that student wins a silver medal. So let's see. This is an example of a permutation, and the number n, that's how many are in my pool. In my example, that would be 8. And from among those 8, I'm going to award 3 medals. So this is a permutation where I have 8 objects. I'm going to choose 3. So that's 8P3. So the formula says that I should take 8 factorial and then divide that by 8 minus 3 factorial. So that looks like this. So that's 8 minus 3, that's 5 factorial. So I have 8 factorial over 5 factorial. So that means 8 times 7 times 6 times 5, down all the way down to 1, all over 5 times 4 times 3 times 2 times 1. Now notice that when I do this, a lot of these factors are going to just cancel out. Everything below 6 in the numerator, the 5, 4, 3, 2, 1, appears in the denominator, 5, 4, 3, 2, 1. So this 5 cancels with this 5, this 4 would cancel with the 4, all the way down the line. My whole denominator just cancels out. So all I'm left with is 8 times 7 times 6. And I don't know what that is off the top of my head, but 8 times 7 times 6. It turns out there are quite a few ways of doing that. There are 336 ways of filling these slots. Now, another way to look at it is, if I have 8 students and I'm going to pick a student to award a gold medal, then I have 8 candidates for the gold medal position. Now, once somebody wins the gold medal, I'm going to take them out of the running. And so if I consider how many students I have left to consider for silver, there are just 7. And then, once I award the silver medal, I should have 6 students left to consider for the bronze. And so this is another way of thinking about this problem. Just 8 times 7 times 6. You get the same answer as when we use the permutation formula. And if I were just to select students to maybe come to the front of the classroom and present to work a problem, and everybody was going to work the same problem. Maybe I was going to have, a whiteboard, and I, have was going to write an identical problem like this. Okay, so I wrote up on the board the identical problem: 3x plus 1 equals 10, 3x plus 1 equals 10, 3x plus 1 equals 10. And I'm going to pick 3 students to come to the front of the classroom to do this. So one person is going to stand here and work the problem, another person here. Now, if you're selected to come to the front of the classroom, it's probably not going to make any difference to you whether you're in this position, or this position, because everybody's working the same problem. Now, I still have 8 people in my pool, and I'm still going to choose 3. However, in this case, order does not matter. So this is an example of a permutation, or of a combination. And so for this, we turn over to page 238, and we see a different formula. It looks very similar to the permutation formula. There's only one little difference. So I have n choose r, or this is a combinations where I have a pool of n, and I'm going to select r objects. I still have n factorial in the numerator. I still see an n minus r factorial in the denominator, but there's another factor of r factorial. So in this case, if I have 8 objects, and I'm going to choose 3, I have 8 factorial over 5 factorial, 3 factorial. So the 8 factorial, that's the n factorial. I still see the 5, that's n minus r, and the 3. In a combination, these factorials in the denominator, notice 5 and 3 add up to 8. I'm kind of partitioning the 8 students. 5 are not selected to come to the board, 3 are selected. Now, this is, it would be the same answer if I said 8 choose 5, because this is multiplication and that's commutative. So in this case, we'll get 8 times 7 times 6, 5, 4 times 3 times 2 times 1 over 5 factorial, 5 times 4 times 3 times 2 times 1, and 3 factorial, 3 times 2 times 1. So here we are. Now again, a lot of things cancel. The 5 factorial still cancels with the 5, the 4 cancels with the 4, the 3, the 2 and the 1, and the 2 and the 1. I still have an 8 times a 7 times a 6, and 3 times 2. So from our previous work, 8 times 7 times 6, that's 336. And in the denominator, 3 times 2 is 6. So now we go 330, what was it? 336 divided by 6 is 56. So notice it makes a big difference whether you use the permutation formula or the combinations formula. In the permutations example, where order matters, that's where there was significance to the place. Gold is different from silver, which is different from bronze. In that case, there were 336 possibilities. Now, in the combinations example, I still have a pool of 8 candidates. I'm still selecting 3, but order doesn't matter. It doesn't matter. There's no distinction between this position, and that position. So I end up with a lot fewer possibilities, 56, as opposed to 336. There are 1/6 as many. Now, of course, those numbers, those were the numbers specific to this example. But that is just a quick little preview of 4.4. What the key concepts are, how to do you need to know how to calculate a factorial, and then you'll have to just kind of memorize the 2 formulas, one's for permutations and for combinations, and then be able to recognize when it's appropriate to use which formula, whether your scenario calls for permutations or combinations.
Awesome. Yeah, what you just showed made sense with the different formulas. So.
Okay, good.
Hopefully I get this.
Actually, since we've got about maybe not quite 15 minutes, I'm just going to kind of randomly pick an example from the book, and let's talk through it together and see if we can figure out if we should use the permutation formula or the combination formula. So let's see. Let's see. Okay, yeah, let's do. I'm just going to do number 24. Again, I'm kind of just trying to pick one where it's a permutation or a combination. So now again, I'm reading from the 6th edition. So, but this says that you have a foreign language club, and they're going to show a 4-movie marathon of subtitled movies. So how many ways can they choose 4 from the 11 that are available? Now, basically you've got 4 slots to fill. Now, I want to show you a variation on this problem. We're going to do it both as a permutation problem and as a combination problem. I want to highlight that you really need context to know which is which. Now, let me say that we're going to show one of our movies at 3 p.m., one of them at 5 p.m., one of them at 7 p.m., and one of them at 9 p.m. So I have 4 slots to fill: the 3 p.m. slot, the 5 p.m. slot, the 7 p.m. slot, and the 9 p.m. slot. Now, in this scenario, being in the 3 p.m. slot is different than being in the 9 p.m. slot. And you may think, oh, well, maybe the 7 o'clock, maybe this is real desirable. Everybody wants to be in the 7 p.m. position. But either way, I've attached significance to the time slots. Now, in this case, when I think about the possibilities, because the order matters, this is a permutation problem. And so
Right.
I would use the permutation formula where I have 11 possibilities. I'm going to choose 4, and the ordering matters. So that would be 11 factorial over 11 minus 4 factorial, so 7 factorial. So you would end up having to do this calculation. Now, remember that, so this means 11 times 10 times 9 times 8 times 7, da 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 da. And this is 7 times 6, da da da. Everything in the denominator is going to cancel with factors in the numerator. You're really just going to end up with (11 times 10 times 9 times 8). There are 11 possibilities of things you could put in the 3 p.m. time slot. But once you've selected something for 3 p.m. and you're trying to fill the 5 p.m. slot, there are just 10. And then there are just 9 and then 8. So the product is how many, you need to multiply these things together, which I'm not going to take the time to do, but that would give you the answers to the permutation problem. Now, if you're just going to pick 4 movies and just say, these are the 4 movies that we're going to show, and maybe you're going to end up just listing them in alphabetical order, no matter what's selected, then in that case, I'm going to just make this as like a comma separated list. So this is what we're going to put on our flyers maybe. We're just going to list the 4 movies, and really the order that I list them, that's not necessarily the order that we're going to show them, or doesn't give one any kind of higher ranking or billing. It's just, here are 4 movies. We're not even sure, when we're going to show them or where, but we have made the selection of 4. In that case, we have a combinations problem. That's 11, choose 4. So again, you're going to have 11 factorial, and in the denominator, you still have 11 minus 4 factorial, but also another 4 factorial. So that looks like this. 4 choose, or 11 choose 4, 11 factorial over 7 factorial times 4 factorial. So once again, you'll have 11 times 10 times 9 times 8, because that's just the same as these numbers. But there's going to be a denominator of 4 times 3 times 2 times 1. So you take 11 times 10 times 9 times 8. You get 7,920 over 4 times 3 times 24 over 24. So here's what that works out to be. In the permutations problem, that would be the 7,920. In the combinations problem, though, that's divided by 24, and there are only 330. So notice there are a lot fewer possibilities in the combinations, when the order doesn't matter. And in the permutations problem, there would be 7,920, and then the 330. Now, the way that this problem was phrased in the book, choose 4 from the 11 available, the answer would be just the 330. But I wanted to show you how you could make just a slight change in the phrasing, and it switches from being a combinations problem to a permutations problem. You have to just ask yourself, is there significance attached to a position? Is being listed first somehow different than being in the second position or the third position?
So, because we've got the same problem in our book, so just looking at it, because it doesn't ask for a specific order, That's how you determine if it's a combination problem.
Yeah, this is the way this reads in the book. It is and actually I have the answer in front of me. I know that the correct answer to this problem is 330. They definitely intended it to be a combination problem. So they're just saying pick 4, and you're not saying put them in order 1st through 4th. Now you're just picking 4 to show, and not really saying anything about time slots, or maybe in some film festivals you award medals like a blue ribbon or a gold medal. No, they're not saying like that. They're just, you're going to pick 4 to show and leave it at that. So this is a combinations problem.
Okay, awesome. Thank you.
Yeah. And just be aware that even though I've done these, for 20 years now, it's still tricky to figure out when you read these problems, whether it should be a combinations or permutations. So don't be upset or frustrated if on your first couple that you think it's a permutation problem, but it ends up being a combination problem. I mean, it's not easy. So don't be too hard on yourself. But and certainly if you're not sure or not sure why it's one over the other, you can definitely send me an email.
I will do that. Thank you.
Yeah.
I'm sorry, which problem are y'all working on?
Oh, that was, I just kind of picked one from the textbook. It wasn't, I don't know if it was actually among your homework problems, but I just chose as an example. That was number 24 from section 4.4.
It's page 236, if you guys are interested.
Okay, thank you.
Let's see. Well, it's almost, we've got a couple minutes left. If you guys have any other questions, let me know. And if we went a little over, that's fine too.
I don't know about anybody else, but I am not like an algebra math person. I'm struggling with all of it. Any of it you want to talk about, I will listen to.
Okay. Well, Marie, what did you have? I mean,
I've been working on the homework questions.
Yeah.
And kind of fumbling my way through and looking in the book and listening to the lectures and trying to piece together. But I haven't had a math class in probably 18 years.
Yeah.
So.
As a current student myself.
Yes.
45. I know what you're. I understand.
The nursing part of it comes super easy to me. If I just had to do nursing classes, this would be awesome.
Yeah.
But putting me in a math class gives me anxiety.
Yes.
So
no,
any part of it you want to talk
about? Okay, yeah. I tell everybody though, with statistics, I really don't, I think it is one of the most useful math subjects across the board because in nursing, I'm sure you'll come across research where they have probabilities, and so everybody's got to be able to make sense of data, and so that's I really think you will find it useful. So, but even if it doesn't come as natural as just the nursing content, I do think you'll find it relevant someday.
Okay.
I have a question about section 4.2
and the mutually exclusive probability formulas
Yes.
and the ones that aren't mutually exclusive? Yes.
Yeah.
If you're taking the probability of A or B and you're adding them together,
Uh-huh.
and then you're subtracting, and it says subtract the probability of A and B, don't you always get 0?
No. Let me. In fact, I can explain this. I got this
Okay.
one. Okay.
Because on the homework, I came up with 0 on both of those, and I'm like, how can it both be
If you had
0?
a,
I don't understand that.
what specific problem were you looking at? You know, can you tell me?
It was question 10.
In 4.3?
Question 4.2.
4.2, okay, I need to go back.
Yeah, it was actually question 10 and question 17.
Let's look at
Both
question
of those.
10. Now, again, I'm using a 6th edition book. So in my question 10, it has to do with selecting a card. Is that the same for you?
Yeah. Yes.
Yeah.
Yes.
And mine says a single card is drawn from a deck. Find the probability of selecting the following. So in part A, in my textbook, it says a 4 or a diamond. Is that what you have?
Correct.
Okay, now.
Yes.
Here's the notation, just so that I'll get easy. I think the probability that you would get a 4 or a diamond. Now, first of all, let's ask ourselves, are those two things mutually exclusive? Is there any way for those two things to happen at once? If you only pick one card, is it possible that you'll pick both a 4 and a diamond?
Right, yes.
Yeah, because there is a card out there. Namely this guy, the 4 diamonds, that is both of those things. So these are not mutually exclusive. So this is where we need to take the probability of a 4 plus the probability of a diamond, and then we need to correct for that overlap. Correct for the fact that we could select a 4 and a diamond. Can you see here? So I'm saying we need to find the probability that you would select 4, probability that you would select a diamond, but then we need to subtract off the probability that you would select the 4 of diamond.
Okay.
So let's fill in these probabilities. How many 4s are there in a standard deck of cards?
4.
Yeah, okay. Out of 52,
13.
right? Uh-huh.
Oh, I'm 52, yeah.
How many diamonds are there?
13.
Uh-huh. And how many 4 of diamonds are there?
1.
Just 1, right? Okay, now.
1.
So here's the probability that you would get a 4. There are 4 out of 52. Here's the probability of a diamond. There are 13 out of 52. And then the subtraction here, this is my correction factor. That means, see, I've double counted the 4 of diamonds. It's included among the 4s, and then I included it again among the diamonds. So I counted that card twice.
Oh.
So I'm correcting for that by subtracting it off. So I take 4 plus 13, which is 17, but then I subtract 1, so I end up with 16 over 52. Now, those are both divisible by 4. So when I reduce this down, my final answer is just 4/13. Now, how did I get the 4/13? Again, I take 4 plus 13, that gives me 17 minus 1. 17 minus 1 is 16. These had a common denominator of 52, so I could just do the addition and subtraction. 16 over 52, I can reduce that branch to 413.
Okay. So I think I've got those wrong then. So if you, because I thought the 4 and the diamond would be mutually exclusive. And I don't know why I thought that.
Now, let me ask you this.
Maybe I
What
got
if
it
said,
backwards.
what's the probability of getting a 4 or a 7? Now,
Okay.
is there one card that's both a 4 and a 7?
No.
No. That's mutually
No.
exclusive. If you get a 4, you didn't get a 7. They can't
Okay.
happen
So
simultaneously.
those are mutually exclusive?
Yeah, but now a 4
Okay.
in diamonds, that can happen because there is a 4 of diamonds.
Right.
So you can have both things happen at once, whereas you can't have a 4 and a 7 in a single
Right.
card. So
Okay.
the 4 and 7 are mutually exclusive, but the 4 and diamonds are not.
Okay.
Now-
So I just got those back. Yeah.
Yeah. Now, when you were saying, are you always going to get 0? Now, in this case, when I probability of a 4 plus the probability of a 7, and then I subtract off the probability of 4 and 7. Let me make a few notes before I put this up here for you to see.
Because when they're mutually exclusive, you don't subtract. Is that correct?
Well, I just want to say, if you did, it wouldn't change it
Yeah.
because there are 0 cards that are a 4 and a 7. So
Okay.
the correct, what I'm calling a correction factor here that you subtract off is just
Uh-huh.
0. When they're
And that's
mutually
what I did wrong
when they're mutually
was I
exclusive,
added. Okay.
yeah, when they're mutually exclusive, this is always going to be 0.
Okay. Okay. I think what I was doing wrong is I was adding A and B. So I was adding, like on the, so the one was 4, I was adding those two together and putting them over 52. And if you're subtracting that too, then you're always going to get 0.
Oh, yeah, true. Then you would always do 0. That and that you're subtracting means simultaneous, but it's both at the same time. So you've got the probability of 4s, the probability of diamonds, and then the probability that in a single card, you would get both a 4 and a diamond. That's just 1.
That's it.
Out of 52.
Okay. That makes sense then. Yes.
Yeah. Well, okay, so it's already a little past 9, so I think I'm going to end the recording there. Thanks so much. If you guys have questions, remember you can always send me an email.
All right. Thank you very much.
All right. Have a good night.
You too. Bye-bye.